G'day guys, welcome to your very lucky last video on Year 12 further maths content. Congratulations for making it this far. It was very exciting and it is not an easy thing to do, especially during the remote learning period. So today we are going to go over part 2 of 10.5 on the Hungarian algorithm, which largely looks at allocation problems like we looked at in yesterday's video. However, this is quite a bit of a process when certain things are happening in our question, which we'll look at now. All right, so yesterday when we looked at the basic allocation problem, what we needed was when we drew our horizontal and vertical lines in our matrices or in our tables, we needed the number of lines to be equal to the number of tasks that were allocated in that problem, the minimum number of lines that we could possibly draw. So sometimes when there are not enough zeros or there are too many zeros, this is when we need to allocate the Hungarian algorithm. So there's a bit more of a step-by-step process here. Make sure these notes are written down in your workbook when we move on to the next slide. We're going to do a full Hungarian algorithm question, which is quite long, so you will need these steps written down. Starts off the same as the allocation problem, where we draw a matrix or table. Then we perform a row production, so we find the smallest value in each row and subtract it from all numbers in that row. Cover the zeros with the minimum number of lines. So if that matches up with the number of rows, then yeah, cool, jump to step 7 like we did with yesterday, but if not, that's where we continue with step 3. With step 3, we perform a column reduction where we find the smallest value in each column, then subtract it from the numbers in that. Again, we cover the zeros with the minimum number of lines. If that matches the number of rows, the number of tasks, cool, go to step 7. However, if not, we continue with the steps. That's where we begin the Hungarian algorithm with step 4. What we do is we find the smallest uncovered number in our whole matrix after the row and column reductions have already been applied. We add this to all covered numbers in the matrix from step 3, and then at any intersections of line that we've had from the previous step, we add that number twice. After that, we subtract the overall smallest number from all numbers in the matrix, cover the zeros with the minimum number of lines, and hopefully by that time we've reached optimal allocation by having equal number of lines to how many tasks. So there's quite a process involved with the Hungarian algorithm. I'm going to move on to the example in the next slide, so if you haven't finished writing that down, make sure you pause the video and get those steps down. All right, so here we have a question. Amy, Beth, Kate, and Dana offer quotes on how much of each of them will charge to complete 4 different jobs, P, Q, R, and S. The table summarizes these charges in dollars. Use the Hungarian algorithm to minimize the total cost to complete the 4 jobs, with one person doing each job. So on the left there, with the filled-in table, is the 4 jobs and the 4 people involved. So Amy charges $17 for job P and $24 for job Q, etc. You can see here I've drawn 4 tables. That's because we are going to be filling in all 4 of these to do the full Hungarian algorithm, so it is quite a process. At the end, we're going to draw a bipartite graph and then work out the most optimal allocation of jobs to minimize our overall cost. All right, so the first thing, we already have a table here to represent our problem. That's step 1. Step 2 is to perform a row reduction. So what we need to do is look at each row, subtract the smallest value in that row from all numbers inside of that particular row. So in the first one, 17 is the smallest value, so we're going to be subtracting 17 from all numbers in that row. Row 2 is 18. Row 3 is 14. And finally, row 4 is 11. So we need to go through and now subtract all those from the numbers inside those corresponding rows. So we're going to draw that in our first table here. 0, 7, 25, and 4. So we subtracted 17 from all those numbers in the first row. Second row, we have 7, 0, 1, and 2. So we've subtracted 18 from all of them. Third row, we have 15, 0, 17, and 8. So we've subtracted 14 from all of them. And finally, last row, subtract 11 from each number. Which leaves us with that. All right, so now with step 2, we also need to draw in the minimum or the smallest possible number of lines to cover up all the zeros. So if we do that, we would cover those two and these two. And all zeros are now covered. We've managed to cover all zeros with only 2 lines. This does not match up to the 4 tasks. Therefore, we do need to apply the next step. So step 3, we perform a column reduction. I'm just going to remove those lines so they don't get in our way too much. All right, so looking at this second table now, we're going to perform a column reduction. In the first column, the smallest number is 0. So we're going to be subtracting 0 from each of those. Same thing with the second column, the smallest number is 0. In the third column, the smallest number is 1. And in the fourth column, the smallest number is 2. So now I'm going to fill in this second table, applying those changes. The first 2 columns are unchanged because we just subtracted 0. From that third column, we have subtracted 1 from all the numbers. And finally, from the third column, we're subtracting 2, which leaves us with this. All right, so again, we are going to try and cover the zeros with as the smallest possible number of lines that we can. There are a couple of ways that it could be drawn. I'm going to cover those first 2, those 3, and this one. All right, so I've covered all the zeros. I've only used 3 lines. Again, that's not the same number of tasks that we have, so I haven't finished my allocation here yet. So what I need to do is move on to step 4, which is to apply the actual Hungarian algorithm. So looking at the table I've just drawn over, I need to find the smallest uncovered number, and I need to add this to all covered numbers in the matrix from step 3. And at any intersections of line, we add the number twice. So looking at the previous table, the smallest uncovered number I have is the number 1. So I need to identify that. Sorry, my mouse has just gone a bit funny. So that's my smallest uncovered number. So now what I need to do is to just add that to every single covered number except for 15 and 7. I'm going to add it twice because there is an intersection there. All right, so going through, that top left was 0, so I need to add that 1. 7, 24, and 2 are uncovered, so we don't need to do anything to those. In the second row, we have 7. There's an intersection there, so I need to add the smallest number twice. And then these zeros, we add 1 to it. 15, I have to add 1 twice. And then once to these covered numbers here. And finally, we have 1, 9, 5, and 2. All right, now that I've applied that, I need to move on to the next step. Step 5 is to subtract the overall smallest number from all numbers in the matrix. So the overall smallest number in this case is the number 1. Look, I realized I've just made a little mistake in the previous one. That's 2 in the bottom right. That shouldn't have been 2, that should be 1 because it was uncovered. All right, sorry about that. Okay, so the smallest number in the entire new table is the number 1. So we now need to add that to every single, subtract that from every single number. So write that in our new table. Which leaves us with that. So that was step 5, to subtract the overall smallest number from all numbers in the matrix. Cool, so with step 6, we apply the lines to it again. Again, we are trying to cover it with the minimum number of lines. All right, let's see, how can we do this? We can do it like that. So there's a few different ways that you can draw it, but how it is currently, it can't be done in any less than 4 lines. Therefore, that's good. The number of lines required to cover the zeros is equal to the number of tasks. We can now move on to part 7, which is actually answer the question. I'm going to convert this into a bipartite graph. So on the left here, we had person A, Amy, Beth, Kate, and Dana, performing tasks P, Q, R, and S. So now looking at the table in my final one I've just drawn, in Amy's row, she has a 0 only at P. So I'm going to draw a line from A to P. Looking at Beth's row, she has 3 zeros at Q, R, and S. So I'm going to connect those up. Looking at Kate's row, she only has a 0 at Q. Should probably have arrows on these. And finally, at Dana's row, she has a 0 at P and S. That's my bipartite graph. Last thing to do is just to simply allocate them now to a task and therefore work out the overall cost. So for Amy, she only has an arrow to P, so that's definitely the job that she has to do. Oops. And that in the original quote was $17. Because Amy's doing P, that means Dana has to do S, because Dana only had a 0 for P and S. Sorry. And that had a cost of 14. Kate has to do Q, that's the only one she has a line to. And she is quoting 14 for that, which means finally that Beth has to do R. And she is quoting 19 for that. So for the total, we would add those up. So 17 plus 14 plus 14 plus 19 equals $264. So that is the minimum cost to complete the 4 jobs if one person was allocated to one job. So it is quite a process, this Hungarian algorithm. There's a lot of steps to it. Like with anything in this topic, just practice, practice, practice. And yeah, that's about it. Well done, guys. Thanks for that.